Yeah.
Now it is live in YouTube. Is it? Where is Dr. Monpuya?
It is live, sir.
It is live in YouTube now. Is it? Okay. Can you transfer the host to me once again? If you have, yeah, the meeting is being live streamed. So I have made Professor Sugata as a co-host, and okay. Now all the technical settings are done. Now I think I should pass on to our chairman for this session, Dr. Sivraj Guru.
Hello, good evening, my fellow participants, and very good morning to our distinguished speaker, Professor Sugata Chaudhary from USA. So it's nice to have you, sir, with us. The special talk, this session will have a special talk of 1 hour duration, which will be the talk delivered by Professor Chaudhary for 50 minutes, followed by a short discussion session. If any participant have questions, they can raise the questions during the discussion session. Before we start with the talk, let me give a brief introduction of Professor Chaudhary. Professor Chaudhary is presently working as professor in Department of Physics and Astronomy, Harvard University, USA. Professor Chaudhary did his MSc from Pune University, India, and obtained his PhD from Calabria University, Italy in 2009 in theoretical computational chemistry. He is the recipient of Bernardino Telesio Fellowship in Earth Science for the year 2005 to 2008 from University of Calabria, Italy. Professor Chaudhary was also awarded the MML Postdoctoral Fellow accolades for exceptional contribution in the field of computational material design with focus on quantum mechanics by NIST 2019. He has a varied research interests. His research interest focuses on quantum information, fermions, and chiral magnetic materials, topological insulators, transitional metal dichalcogenides, transition metal oxides, and graphenes, among others. Professor Chaudhary has good number of publications in reputed journals such as Physical Review Materials, ACS Applied Nanomaterials, Physical Review B, Applied Physics Letters, and many more. We are very fortunate to have you in our midst, sir. And may I now invite Professor Chaudhary to deliver his talk on effect of thickness, external magnetic field, and chemical substitution on the quantum phase transition of intrinsic antiferromagnetic MnBi2SC4 and the family of materials. Professor Chaudhary, sir, you can begin the talk.
Thank you. Good evening, everyone and participant. And I really appreciate for your invitation. I am really honored to be a part of this conference, and I would like to discuss my recent work. The title of talk, I would like to also thank all of the organizers to giving me the opportunity to present my work here. Title of my talk is the title of my talk is the effect of the external magnetic field and chemical substitution on the quantum phase transition of antiferromagnetic manganese bismuth solenoid and the family of materials. So here I would like to present whatever I have done for the last 3 years and with my colleague and my collaborator. So first, if we go to the deep, I would like to thank my collaborator, my NIST collaborator, Francesca Tavaza and Kevin Garrity, Then from TIFR, India, Bahadur Singh, and Northeastern University, Professor Arun Bansal, and the postdoc from there, Borun Ghosh, Bao Kai Wang, and PhD student Matthew Matchell. Also, I would like to give thanks to my experimental collaborator from Rutgers University, Sean O, for the transport measurement, Kurt Richter and Joe Hagman, and the experimentalist for the Raman from NIST, Angela Hyde Walker. And also, I would like to thank my another collaborator from SLAC, Stanford University, Josh Turner, and my student, Gadir and Devojyoti, the PhD student, Alana Jalen, and Salia, the undergrad student here. The question is that, why do we need that magnetic quantum material and why so important? If you will look the evolution of the computer or any electronics things, first we use for our computer vacuum tube. Then we used transistor. It slowly became smaller, and now we are focusing a 6 atom device, which could be revolutionized and which could be make our communication faster in these cases. So recently, there are focus on what is called the quantum computer. There are 3 different quantum computer as developed. One is Google quantum computer, Microsoft quantum computer, and IBM quantum computer. But the development of the quantum computer hindered by the proper material, which could be useful for the quantum computer. What is the quantum computer and how it is working? Here, if you notice that this is the paper recently the IBM published in Nature Electronics. Here it is showing that there is a here topological qubit, then cryogenic control, and the room temperature control, and there is a quantum classical interface, and then classical computer, and this we can work and the workstation, and we can communicate with the quantum computer. The problem is here that is the development of proper topological qubit. And for that quantum topological qubit, why need that? Whatever the quantum computer we have a noise, and it could be problematic. It is not fast enough, but they cannot handle a large number of calculation. It is faster, all those quantum computer. My focus of work area to find out a material which could be useful for the topological qubit. So here I would like to mention basically, when we are saying the material, we have to focus on we need a low cost and energy saving material, which could be useful to at higher temperature. Whatever the material we have, it is very low temperature, around 10 Kelvin, I can say that, and it could be not be barrier for us for the development of the quantum computer. So what is recently found out that after the development of the topological insulator, there is few material is making really good progress that which could be useful, and one of the class of the material is called the magnetic topological insulator. Here basically I would like to present all the 5 paper whatever we are we published, and we are working on that particular focus of the area, that is MNP, manganese bismuth solenoid structure. So what is the manganese bismuth structure? This is septuple layer. So here it is magnetic material manganese. This is the solenoid, bismuth solenoid, and similarly opposite. If you will notice that this material completely, if you will put a mirror, it could be completely inverse. So it is image, up as down is image. But how and what is the important, what is the property, magnetic and electronic property, we have to understand before application of this material into that any kind of nano or basically the quantum computer. So this focus will be three part. One part is the magnetic phase and property of manganese bismuth solenoid. Then magnetic domain wall we have to discuss, and then we will discuss the chemical substitution, how we can manipulate the property of the manganese bismuth solenoid structure. So let us consider first how the development is going on. Hello, do you have any question?
Sir, let me interrupt and make a few announcements. I request all the participants to mute their sound. So even though I'm monitoring from here, so if you accidentally turn on your microphone, it disturbs our speech, our talk here. Thank you, everyone. Please, sir, continue.
So in this case, I would like to let you know that one of the most important development in recent year, the finding of the topological insulator. In this case, I would like to let you know that I am very fortunate I got a chance to work with Professor Charlie Kane and Eugene Malley, who was the inventor of this kind of topological insulator. So here I would like to let you know that what is the first topological insulator. It means predicted by theoretician and growed and experimentally observed. That is that bismuth solenoid, bismuth telluride, and antimony telluride. If you notice that one, there is Dirac cone. All this red part, it is according to the electron, and all this blue is then there is no electron part. So if you notice that, this is like a metallic, but we can manipulate all this structure and depend on the chemistry of our material or atom. If you notice their band structure, it is changing. So here I would like to say that that is the major what is called the major development for the topological insulator. Here is the another group who's predicting the bismuth solenoid structure, and they said that how the spin orbit coupling and spin orbit coupling, that means full relativistic effect, is playing the role for the electronic property of the material. And after that, there were two different groups also synthesized the bismuth solenoid structure, and there was experimentally observed by the two different groups. So it is given indication that that is possible, about that we can, using the mother nature kind of electronic property of the material, so we can develop different kind of topological material. The question is that these materials are not magnetic. These materials are all non-magnetic things. So what we can useful that magnetic atom, because any kind of electronic or quantum material or quantum means computer development, we need magnetic topological insulator. So why would we need the magnetic material? Because it is the giving us the another state, which is called quantum Hall and quantum Hall anomalous Hall effect. What is the showing that the figure? This is the paper published by one of my friends, Sean O from Rutgers, and he explained in little bit detail about that what is the difference between the three of that, more the property of a material which could be useful for development of quantum computer. So here, this is the H propagate single direction. If you notice that H is propagating spin up and spin down, it is propagating. So no possible scattering if there is a bulk is insufficient or insulating. On the other hand, the quantum spin Hall effect, H propagate in both direction. So if you will notice that this is the H propagate, and in both direction, spin down is moving in one direction, spin up is moving opposite direction. Scattering is possible if the spin flip. So what is the requirement for this kind of quantum anomalous Hall effect? 2D ferromagnetic topological insulator. That means you don't need any kind of external magnetic field. It must be topological, so the dissipation analyze each state which could be we can observe, and it should be insulating. So only each state can transport, and there is anomalous Hall coefficient is quantized by this number C, which is called the Chern number. The problem is to get this kind of material, that most ferromagnetic material until experimentally developed are metallic, and magnetic order is difficult to realize in 2D system. And another thing, magnetism and topology cannot go together. It is what may be against each other. So what happened after the prediction of the bismuth solenoid structure? Jahid Hassan group developed a method. They doped the system, and with dope the system by the magnetic, they observe the topological quantum anomalous Hall effect. There is another group also doped the system by chromium atom, and they also notice that they are getting the band gap open. So it is behaving like an insulator. So the question is that all this experimental work has been done when the temperature is very low, and in these two cases, the temperature is 1 Kelvin. The question is that if it is 1 Kelvin, so practical application, it is really tough. So for a useful practical application, we need that higher temperature, which can operate and show that this kind of property. Second thing is that we need larger band gap, and third is robust single crystal. So that was the development was going on. In these cases, first I would like to go to that, it should be MNBS2, and then we will go to the domain wall of MBT. So here, why I mentioned the family of MBT, because MBT is one of the focus area for the experimental theorist and material science or engineer, whatever, because it is easily synthesized. And it is that when 2018, I was presenting my talk in APS, that there is only 4 presentation were there, but 2019 and after that, they created APS 2 session and huge number of magnetic topological work started to come out on the surface. So here we would like to do, first we look at the periodic table. When we look at the periodic table, vanadium, chromium, manganese, iron, cobalt, and nickel, all these material are magnetic. But interestingly, manganese chemistry and the hybridization process created opportunity to develop a topological insulator. So manganese bismuth solenoid structure has a 2 different symmetry. One symmetry is C2M, another symmetry R3M rhombohedral structure. It is known that the C2M symmetry is trivial insulator, and R3M symmetry has the non-trivial insulator. And the question here, most of the important thing is that naturally MBS or manganese bismuth solenoid can create that C2M symmetry, or ground state is C2M symmetry. To synthesize a single crystal, it is always moving towards that direction. So create a R3M, which is showing different kind of topological property, you need thin film synthesis or MD growth. So in NIST, my collaborator, Joe Hackman, has developed a method, and they synthesize the material bismuth solenoid quintuple layer and bismuth manganese solenoid septuple layer. Actually, that is the first development of any kind of manganese bismuth solenoid structure synthesization process. And after that, our collaborator, it is saying that this work, the development of MBT or any kind of work, is actually initiated, and it is encouraged the scientific community to synthesize MBT or manganese-based master telluride and other material to grow. And after that, it started focus on the MBT, because MBT can be, manganese-based telluride can be synthesized in single crystal. So let's go, what is the difference between bismuth solenoid and bismuth manganese solenoid structure? If you look at that, both the structure is rhombohedral, but here it is a quintuple layer 1, 2, 3, 4, 5. And here it is septuple layer 1, 2, 3, 4, 5, 6, and 7. And they are hexagonal, means these two structure is similar, but here the difference is this is the magnetic system and this is the non-magnetic system. Otherwise, the symmetry of both that structure is same. So what we did, first we find out if there is non-magnetic septuple layer is possible or not. So what we did, we noticed that there is a gamma point, we are getting band inversion, and here this is the local density of state for that material, and it is showing that how the formation of the Dirac cone of the manganese, bismuth lead solenoid system. So we first focus on that material, and then I was saying that, okay, if we will replace the lead by the manganese, what will happen? So as we know, any kind of material, it is going to be magnetic. There will be two possibilities, ferromagnetic and antiferromagnetic system. So when we find out its ground state is showing that manganese-based solenoid structure is actually an antiferromagnetic system ground state. So that means we can apply the magnetic field external and we can modify the property of the system. So what is going on? What is the things we found? Its ground state is antiferromagnetic, and it is showing that axion insulator. But on the other hand, if you will look at the band structure, ferromagnetic and antiferromagnetic, antiferromagnetic is the insulator and there is a band inversion. But on the other hand, the ferromagnetic system is a semi-metallic system, and there is, if you notice that the band crosses around the gamma point, 2 point, different point, and that 2 point is actually called the wild node in the front, and from these called wild semi-metal. So which direction is our magnetic system? If you notice that our magnetic moment of this manganese system, it is out of plane. But the question is that we cannot, it is showing into the magnetic field along that, the out of plane, along the z direction. Is it possible that property will change along if we will apply the magnetic field in plane? So what we did that magnetic moment out of plane and magnetic moment in plane direction. You notice the semi-metallic behavior of the material is not changing. Previously we got 2 nodes, and here we are getting while there is a circle which is called nodal line, while nodal line. So this is their semi-metallic behavior is not changing, but changing what? Their band structure. And that is giving us that magnetic ferromagnetic phase of this MBS is really it is a very good candidate for different kind of application. What we find out, while node and pair of opposite chirality, and while node are protected, and while node look like a pseudomagnetic monopole in momentum space. Unusual surface state, Fermi arc, no relation in Fermi arc, that is in the qubit. So what is happening in the Fermi arc? They are connected to each other. When we are working on MBS system, at that time different group has worked on actually the MBT system, and they found similar kind of property for the MBT. And from there, we found out that these material or family of material are really, really good candidate for anomalous quantum observation of anomalous quantum Hall effect. So what we did, we find out that how it is working. What is its transport property? You will notice that this is the surface of a, and this is the structure of ferromagnet, this manganese bismuth selenide structure. So this is the spin up and spin down. And if you notice, there is an even number of layers we consider. When it is even number of layer, it is behaving antiferromagnetic, and odd number of layer, it is behaving the material is a ferromagnetic system. So when we check all our cases, here we find out that when it is an odd number, it is Chern number is 1. And on the other hand, when it is what is called the even number, Chern number is 0. If you notice that transport things depend on the layer number. Here, if you notice that the red line, it is showing us, and the odd layer, even layer, and the blue line, it is showing us the even layer, odd layer. So it is Dirac cone and half integer quantum anomalous Hall effect. C equal to 1 when it is odd, and that means it is in ferromagnetic state, and C0, Chern number is 0 when it is an even number of MBS system we are getting. So what happened if we go from monolayer to the bulk system? We first monolayer system, we know monolayer system is a ferromagnetic system, so started for the in this case, we found out that the depend on the layer, it is actually changing its electronic property. And if you notice that there is a bilayer, there is a no band inversion, but when it is the trilayer, there is a band inversion is happening. Then for the antiferromagnetic system, we notice that trilayer, there is no band inversion. So happening, 3 layers of ferromagnetic has happening as a band inversion, but no band inversion for antiferromagnetic system. Then 4 layer, and we notice that in that case is ferromagnetic beyond the 3 layers, there is topological property present, but in the case of it need to be higher than that cases. And we found out there is 8 state, and this is the 8 state, how it is to different direction 8 state it is showing in our cases. So here we put all those cases when the thickness antiferromagnetic bulk, it is antiferromagnetic Ti, but the bulk while semi-metal depend on the direction of the magnetic field. On the other hand, when it is antiferromagnetic system more than or equal to 7, it is a Chern insulator, and when it is 3 layer, it is a, for the ferromagnetic surface, it is giving a Chern insulating phase. And that way we can conclude that manganese bismuth solenoid structure is a very good candidate for observation of quantum anomalous Hall effect. So here, recently, my work with Bao Kai from Northeastern University, Bao Kai Wang, and Professor Bahadur Singh from TIFR, and Professor Arun Bansal from Northeastern University. Here, Bao Kai did a very good job that in that previous presentation, previous work, I did not discuss about details about that what is the C2M symmetry or monoclinic symmetry is giving us information. So Bao Kai considered both the structure. He considered the monoclinic and rhombohedral structure. So if you will, here I would like to give you the direction what is the antiferromagnetic It is the out of plane antiferromagnetic and in plane ferromagnetic. And this is the ferromagnetic system, out of plane, in plane. And he also considered that cases about the non-magnetic system for the rhombohedral. He also considered that about the monoclinic structure, different magnetic phase, he considered how the magnetic moment direction is changing, A type, C type, and all other different kind of type of magnetic system he considered for the antiferromagnetic. Here he considered antiferromagnetic 3 different. You notice that this is the layer completely up and this layer is completely down direction. But here it is alternate way. And similarly, it is the column wise, this is the column wise, this is the column wise, but 3 different configuration actually considered in this case to understand what is the monoclinic, but because the monoclinic structure is actually the ground state for the magnetic system and single crystal, it is formed naturally. So he found out here energetically it is matching with our previous result that monoclinic plane phase is energetically favored than the rhombohedral phase. And in the rhombohedral phase, that antiferromagnetic phase is out of phase or magnetic moment along the z direction, it is also energetically ground state he first found out, and which is matching with our result. Then he did that this band structure, including the spin orbit coupling and non-spin orbit coupling. If you notice that if we don't include the what is called the relativistic effect, the band gap is different. On the other hand, if you use the phase means full relativistic calculation, that the band gap is changing, and this is the indirect band gap. And from there, we can conclude that the band gap is control or electronic properties effect, or it could making any effect by the relativistic or spin orbit coupling. Then he presented the AFN and similar things we found out that spin orbit coupling is playing a major role for this kind of material electronic property. So he did also that FM phase, similar things, it is going on. The spin orbit coupling is playing a major role for the electronic property of the material. So found out that this is the detailed analysis, what is the application for the monoclinic structure and what is the rhombohedral structure difference. This work is still going on, but here we concluded that the band gap for the monoclinic structure is actually that 0.5, including SOC. So here we can say that although that the stable phase is the monoclinic structure, but we can synthesize the rhombohedral structure of the material. Now thinking about that, as I mentioned, that people were focused on more on the MBT system. Why? MBT system can be synthesized in a single crystal. So what is the recent work? Different group has developed different method. This is the group Ortokov first predicted the possibility of MBT system could be a candidate for the quantum anomalous Hall effect, and same time different group also predicted theoretically, and then different group also experimentally show that it could be synthesized, and they also observe different kind of using the RPS data. Experiment gapless, the difference is the experiment and theory is the recent study observed the gapless state above and below the transition temperature. But theoretically, it is predicted it is gapped at low temperature. The question is why it is the discrepancy between theory and experiment. And here also, they find out high temperature magnet, only high magnetic field, the odd layer system at 0 magnetic field. The question is, why not at zero magnetic field? There is two different questions we focus on. It is a fully spin polarized ferromagnetic state. The quantum anomalous effect has been observed as expected, but the anomalous Hall conductivity at odd layer system observed to be quantized at zero field, and why it is. And several experimentalist group observed that surface feature even below the nil temperature, which is expected to the gap due to the broken of inversion symmetry. So we started looking. So what we did, first we compared the band structure using, we developed a tight binding model. What is the tight binding model? And with the DFT things, we find out that the DFT result and the tight binding model give a similar result. Then we encouraged, and after encouraging development, we focus on the temperature, how that band gap is changing. And here, this is the predict using that model, tight binding model. We found out there is a gap. The gap is reducing, and this is at 100 Kelvin. So this is showing the what is the surface state. Surface state is showing it is going to zero as the temperature is increasing, but the bulk gap is consistent, and also average Chern number is changing with the temperature. So the question finding the bulk gap is not close with the with the temperature bulk, but surface band gap zero above the transition temperature. System is non-trivial, and system is a non-trivial TRS invariant above the transition temperature. So in this case, we are getting actually that expected theoretical thing. And then we found out, we developed a magnetic domain model. So this is the different magnetic domain wall we created, and we noticed that this kind of topological state is localized. And when it is localized, that means when you are doing the experiment, which domain system you are doing, we are observing, that is the most important part in these cases. Domain wall means largest. It is giving us that the magnetic property is depend on the domain, magnetic domain wall inside the system. So summary, it is the tight binding model we developed, which is matching with our experimental results. Bulk gap closer at critical value, magnetic transition surface closer above the TN domain wall topological state. It is working on that, what is going on. The future work is going on, measure the domain wall structure, pinning the defect, that STM domain wall, step each topological state, local probe of the band structure versus temperature, band structure versus temperature, and magnetic field. So this is the different work we are focusing on now. The third part, this is the paper is in preparation now, that, okay, until now we have discussed with manganese bismuth solenoid structure and manganese bismuth telluride structure. The question is that if we will change the chemical structure, the chemistry is changing, is it possible to get similar kind of material? So what is we did, we changed not only the magnetic chemistry of the material, we changed the applied external magnetic field. That means in plane to the out of plane ferromagnetism, out of plane antiferromagnetism to the in plane ferromagnetism, and out of plane to in plane ferromagnetism, how it is working. We got a very interesting result here. So what is this? Here we found out the manganese bismuth solenoid structure is a, when it is flop antiferromagnetic system to the ferromagnetic system out of plane, it is a while node, which is already showed. But the MVT is a non-trivial insulating throughout if we change the magnetic field direction. On the other hand, most important things we found out that manganese antimony selenoid structure is a ground state is antiferromagnetic and it is a trivial insulator. But when we apply the magnetic field, it is a non-trivial insulator. So there is trivial to non-trivial phase transition happening for the manganese bismuth, manganese antimony selenoid structure. On the other hand, the MST, manganese antimony telluride system, it is a wild semi-metal phase it is showing. Then second thing is that what happened antiferromagnetic out of plane to the in plane. Similar result we got in these cases, and we found out that manganese antimony selenoid structure is a wild node. And that is the given us that the manganese bismuth selenoid structure, manganese bismuth selenoid and manganese antimony selenoid structure is actually the similar kind of selenoid is showing the similar kind of robust wild semi-metallic node. And the ferromagnetic structure is, if we change the direction, it is not changing for the manganese bismuth selenoid and antimony selenoid structure. The interesting thing is happening if we change for the outer plane to the in plane, it is showing wild semi-metallic phase. So semi-metallic phase to it is going non-trivial insulating phase for manganese antimony telluride structure. So that is given on that we can conclude that from these things that, okay, if we can control the magnetic field, we can control their electronic property. That means you can tuning the property. There is insulating phase means trivial to non-trivial, then the metallic, semi-metallic to the phase of that insulating phase. And in that case, you can understand that magnetism, the magnetic property, electronic property could be tunable. And most of the important part is here, I would like to mention that manganese bismuth, I'm sorry I did not present that slide here, but the manganese bismuth selenoid phase transition temperature is around 50 Kelvin. On the other hand, manganese bismuth telluride system, that the phase transition temperature is actually 25 Kelvin. So we can say that higher temperature we are getting, and this could be a very good candidate for that. And second thing is that we look also, if we check that spin orbit coupling, that means full relativistic way, how it is affecting. We notice that relativistic effect is very pronounced for in this system. If you notice that here, if we'll apply the antiferromagnetic phase, this is a trivial insulator. That is the ground state. But what happened if we consider the ferromagnetic system? Ferromagnetic system, it is showing that the spin orbit coupling is playing the major role. So from here, we concluded that the chemical substitute can control the property, external magnetic field can control the band gap and the wild point, and spin orbit coupling how the phase transition is occurring. So that means all this material is a good candidate for any kind of application. In this way, I would like to thank all my collaborators and for the computational support. We have to exceed NIST and Brookhaven National Laboratory. And thank you for your attention.
Thank you, Professor Chaudhary, for your talk. And I think it was quite interesting because how you go into the details of the what you call quantum computer, how actually we don't know much about quantum computers, but we could understand that how a small thing can lead to good work, especially in what you call your quantum computer cases. So I now open the session for discussion. If any participants has question, they can pose the question. Professor Chaudhary will be happy to answer your queries.
Can you hear me now?
Yeah, yes, sir. We can hear you.
Okay, another, go ahead.
Sir, I have some basic questions that I missed some of the points. This field is completely new to me, and it is very interesting. Your talk is very interesting, and I like it. And the field is also, I mean, very hot, and it's a very thrust area in current research. Sir, I might be, I think my question is very basic, that I missed few points, like how can we identify like semi-metal and this well metal, or well material, or this Dirac materials and all?
Okay, so I would like to give you that the nature of that one. Okay, hold on, please. Look at that. Here, you can see my PowerPoint?
Yes, sir.
That band is crossing happening here. Look at that at the gamma point. So this is called the Dirac point at that. But here, if you notice that one, I'm going to particularly this one, look at that. It's not happening at the gamma point. It is crossing at two different points. This is the feature for the wild point. But when you changing the magnetic, this is the continuous one circle you are getting. That is called the nodal line. This is called point, and this is the wild line. So while nodal point, while semi-metal, and nodal line while semi-metal. This way you can able to find out that what is the wild semi-metal and not in this case. Is that explain your question? Is that?
Thank you very much. It's very clear now. Thank you.
And I would like to also announce that we are always looking for PhD and postdoc student. If you are interested to work in this field, please send me an email. My email ID is sugato.choudhury@harvard.edu.
Sir, that's very nice of you, sir. Thank you very much. We will post the email in our WhatsApp group to all the participants. And they will contact you, sir, like if they are interested.
Thank you.
Okay, if I may, I have one or two questions. Quick questions.
Go ahead, Bahadur.
Yeah, but I think I have interrupted Divya somewhere in between. Is that? Okay. So basically, you showed by changing the magnetic moment direction theta, right? With that, you are tuning the phase topological state of the system. So it is a little technical question. How exactly you fix the direction of magnetic moments? And because at end of the day, while you get the full self-consistent loop, you will be ending up one direction. So is this a soft magnet or what exactly happening? I'm a little confused.
No, it's okay. So you know that DFT can do a lot of magnetic moment. We can fix DFT means theoretically. It is not possible. And you know our collaborator, Daniel Deso. He's also a RPS guy. And you notice that for them to apply the in-plane magnetic field and out of a certain angle, it is very tough. So they can only apply experimentally out of plane, and possibly they can apply, but the certain angle, it is really, really tough for them to apply the magnetic field. They have to rotate the sample and then they can apply the control. This is the technicality stuff, but it is possible if we can do that one, it could be possible. They are trying to do that experimentally to do that, find out that one. Yes, you're right. Question is really legitimate question actually.
Okay, I mean, even for a theory, because you start with some magnetic direction and then you let it do a self-consistent loop at end of the cycle, it must have to resort to some minimum configuration. So in theory, I mean, is these angles are really resorting to that direction? That
Yes,
I mean, of
actually,
course, we can discuss offline as well, but that's what my question.
Yeah, that's so. What is that? It is theta and phi,
Right.
In the APA. So DFT calculation, what we did, we first optimize, fix the angle, and optimize, did the self-consistent calculation. And from that, we didn't change that angle. Throughout that, we fixed this angle, the self-consistent, and calculate the in. First, we optimize the structure. It is out of plane and in plane. Then we got the ground state structure. We take the ground state structure and only change the theta and calculate the energy.
Oh, I see. So is this the more like a model Hamiltonian calculation?
Model Hamiltonian, yes, you can say that.
Okay. I see. It's clear. Thank you.
Yeah.
Okay.
Sir, there is a question in the chat box from one of the participants, and he actually has 3 questions. He says, can you please explain again the industrial and domestic application of your research? That is question number 1. 2 is, can there be a quantum mechanical tunneling effect between the conduction band and the valence band of the MBTs? And the third question is, do you develop a Schrodinger equation for those MBTs? Is it necessary to develop a Schrodinger equation for this particular research?
Yes, the first thing is that I would like to say that all questions are really good. First thing is that industrial domestic application for yes. That is the first things you have to do that one. The industrial application is hindered because of what is called, this is the low temperature, 25 degree Kelvin. 25 Kelvin, which is a problematic. Yes, if we will able to do that, one of our collaborator is working on to making a device and apply some kind of what is called the equipment which could be observe and do the transport property, all those kind of. Yes, there is a huge amount of industrial lab to the industrial application direction we are working, and it is it will take longer time for the industrial application, definitely. And one of the things, one of my project is now I'm working with IBM to find out that how we can use this material. Means we predicted some material, and Professor Bansal and Professor Bahadur Singh is also involved in that project, that how we can manipulate that material and apply to the real system, the computing system it could be. So that is the completely supported by the IBM. Second question is that, can be there mechanical tunneling effect between the conduction band and valence band of the MBT? We are working on that. We don't have a definite answer. Sorry, I cannot give that one about that one. And the third question is, do you develop a Schrodinger equation? I mean, yes, we develop. Yes, without necessary, we cannot do this modeling. Yes, your question answer is yes, we need to develop a Schrodinger equation. Is that good enough explanation I gave means for this your question?
Yes, sir, it's good enough. Thank you very much.
You're welcome.
So if there is no more question, I thank Professor Chaudhary for an interesting talk. I think this talk will this talk will make us go into this field, and moreover, he's already inviting the participants, those who are willing for postdoctoral works. So all those participants, those who are interested in this kind of work, in his field of work, I think they can always approach him. So with this few words, I thank you once again. Thank you for the real nice talk, and hope we'll have correspondence in future also. Thank you so much. And I thank all the participants who are present here, Professor Bahadur Singh and some others participants. Some of our students are also involved here. MSc students are also right now have joined with us. So I thank you all the participants and the speaker especially. Thank you so much for your time. Thank you, sir. With
Thank
these
you.
words,
And go ahead,
yeah,
please.
Yes, sir. You can say.
I say that thank you, everyone. I would like to say that me and Bahadur work very closely. So if you have any kind of scientific question, you can directly email me and Bahadur. We will try to explain as much as possible. And also if you are applying for any opportunity looking in USA, freely contact us. We will be happy to try to help as much as possible.
Just to add to Professor Chaudhry's comment, obviously we are in TFR always host visiting students and scholars. And obviously we are closely working all over the world. So all students and postdocs are free to write to us. There is no issue with that within country as well as abroad. I think in morning.
Mr. Chairman, sir, may I add a few words?
Yeah, sure.
Tomorrow, I would like to announce our tomorrow's program. Tomorrow at 10 a.m., we are going to have keynote speech from Professor Arun Bansal, and Professor Bahadur Singh will be the chairperson for tomorrow's keynote speech. And at 11 a.m., we will have a plenary talk by Dr. S.K. Varshney, who is the head and advisor of International Cooperation Division, Department of Science and Technology, Government of India. And after that, we will have three invited technical sessions. And in the evening, we will have another special talk. So the plenary talk will be chaired by Professor R.C. Tiwari, who is a senior professor in the Department of Physics, Mizoram University. And for the participants and for all the speakers who are interested to attend the program for tomorrow, the link for tomorrow's Zoom meeting will be again posted in the web WhatsApp group for this conference. Thank you, everyone.
Yeah, I think Professor Bahadur was saying something. If you want.
Thanks. What I was saying, our group is also looking for the visiting students and postdocs all the time. So any participants are interested, they can write to us for short projects as well. And of course, with Professor Chaudhry, we can continue further as well. Okay, thank you. I mean, in morning,
thank you, Bahadur.
It was not clear, so I thought let me mention that briefly now. Thank you.
Okay, thank you, everybody. So thank you, sir. With this, we end the session, and I bid good night to all my participants and to the all the participants who are present here. Have a good night and hope to see you all tomorrow for the morning session at 10 a.m.